Welcome to the Visit Audio Playback training session titled Satellite Interpretation of Orographic Clouds and Effects. My name is Dan Bicus. Jeff Braun and myself will be instructing this particular session, and you can see other contributors listed down here at the bottom. The objectives of this training session are to identify various orographic clouds and also offer satellite interpretation for various events where orography played a significant role. The topics that we'll be dealing with include mountain clouds, such as wall clouds, and we're not talking about the wall clouds associated with severe weather. This is the mountain cloud. And also lee wave clouds, orographic cirrus. We'll also be talking about severe downslope winds, orographic convergence zones, gap winds, and finally the impact of orography on convection. Let's look at a gap wind event in New Mexico. And the situation we're dealing with here is flow coming into this canyon here. In this particular event, the Tierras Canyon that affects Albuquerque out on the other side, you have a Bernoulli effect through the canyon accelerating the flow, and you have gusty winds at the mouth of the canyon here. This is a relatively localized effect where you have higher wind gusts right around the mouth of the canyon, but then they dramatically drop off some distance away from that. The duration of these events is typically between 2 and 12 hours. This is particularly important in dry areas such as the west, where it may have effects on later convective potential, in that you introduce some moist air mass in regions that are typically dry. Here's a topographic map for the case that we're showing. Here's Albuquerque right here, and the feature we'll be talking about is the Tierras Canyon, which is just on the east side of Albuquerque right in here. And what we're going to show here is easterly flow that comes in from eastern New Mexico into the Tierras Canyon, and then you get this gap wind effect that affects the city of Albuquerque. Here's the case from 12 June 1999. We'll start off looking at the observations. These are from 0Z, and you can see Albuquerque at this particular time has dry air mass with southwesterly flow at the surface. Meanwhile, out in the eastern plains, you can see stronger easterly flow and much higher dew points. If I advance along to 3Z, you can see the easterly flow start to set up just east of Albuquerque. And then by 6Z, you see the easterly flow develop in Albuquerque, and notice how the dew points have gone up to the 40s. And then by 9Z, we see 64 over 53, much more moist. And they had winds up to about 30 knots here at the Albuquerque airport. One thing to note here as we look at the 12Z time period here is the observation not shown, the Double Eagle Airport, about 10 miles west of the Albuquerque ob that's showed here, only had winds of about 10 knots. So there's a pretty substantial difference between Albuquerque Airport here, which is close to the mouth of the canyon, and then a location just 10 miles away. So you can get the idea of the localized effects set up by the gap winds here. One of the questions we're left with after looking at the observations is where did that easterly flow come from? And if we turn to the fog product here during the overnight hours, you can see precisely where that easterly flow came from. There's actually quite a bit of thunderstorm activity here in the eastern plains of New Mexico. And with the fog product, you can see the outflow boundaries here very well in the lighter colored regions here, which would be the lower level stratus clouds, moving towards the west. And you can see as that easterly flow meets up with the Tierras Canyon here, the entrance of the Tierras Canyon just east of Albuquerque, right at that time is when the gap wind event set up for the city of Albuquerque. Here's the sounding from Albuquerque before the gap wind event, where you can see a dry air mass in the southwesterly flow that we saw earlier in the observations. We switch over to the period where the gap wind events have now existed here for a few hours, and you can see a much more moist air mass, and you can also see the higher wind speeds coming out of the east here right through the gap. And the thing to note is the depth of the air mass. It turns out to be pretty important. You can see the depth of the easterly flow goes up to about 700 millibars or so, and it's particularly important here because the elevation of the entrance of the Tierras Canyon is at about 7,600 feet. So if it's insufficient in terms of the depth of the easterly air mass, it might not make it through the canyon, and it might not set up a gap wind event. So in this particular case, it was sufficiently deep to set up that gap wind event. Now, the other thing I want to point out here is the moist air mass that we've introduced into the Albuquerque area. Remember, this is a region that's typically dry, and in fact, the models had it dry throughout the forecast period here. And we have this small-scale effect where we introduce moist air into this region that's typically dry, and now we have convective potential to worry about the next day. Usually what happens is a convergence zone sets up just on the west side of Albuquerque, and that acts as the focus area for thunderstorms later in the day. Now let's switch topics to thunderstorm initiation and the orographic effects on convective initiation that is mainly the work of Banta in 1990 here. And keep in mind when analyzing the effects of orography on convection over the mountains that the large scale will dictate if thunderstorms will form or not, and the small scale dictates where and when convection will occur. These mountain flows play a role in convective initiation, but should be kept in mind together with other physical and dynamic processes, such as how much cape do you have, shear, trigger mechanism, and so forth. So it turns out we have these different mechanisms that are important here for thunderstorm initiation in the mountains, and we'll talk about each of these. The first one is orographic lift, and this would simply be forced descent due to upslope flow, where air can be lifted to the LFC when the LFC is near or below ridgetop. Thermal forcing is the effects of elevated heating, where you have a lower pressure over the higher terrain here, leading to flow towards the mountain, and thus you get convergence and updrafts near the peaks, and there, as depicted here, we have the thunderstorms developing. And then finally we have obstacle effects, where you have convergence due to flow interacting with the terrain. It turns out the flow at ridgetop level determines which of these mechanisms plays a larger role. Banta came up with different categories for the ridgetop level flow, and the first category that we'll look at is light ridgetop level flow, which is less than about 6 knots, and of course that's an approximate number. And what he found here is that the thermal forcing is dominant, especially in regions with low soil moisture and limited vegetation, as is typical out west in the Rocky Mountain region. He also found that the solar angle is pretty important, and that you see cumulus initially developed over the east-facing slopes of the highest peaks, and then can be followed by the west-facing slopes later in the day. To illustrate light ridgetop level flow, let's look at this case here from June 2005. And in green here we have the 500 millibar heights to give you an idea of the intensity of the ridge here in this region. And then for the ridgetop level flow, we're assessing the 700 millibar winds here. The region we're going to consider is here in southwest New Mexico, and notice the winds here at 700 millibars are just light and variable, so definitely in the light ridgetop level flow category here. Now we look at the visible satellite imagery for our area of interest here in the conditions of light ridgetop level flow, and you can see right away that thermal forcing is the dominant factor here, where you can see along the higher ridgetops, such as here and then also over here, we see cloudiness and convection occurring here as we get the sun coming up during the day. And you can also see the solar angle effect as well. If you watch this loop, I'll speed it up a little bit more, and just notice earlier in the morning that we have the east-facing slopes predominantly with the convection, and then as we go to later in the day, most of the cumulus is developing on the west-facing slopes. And also notice in the lower terrain areas we're getting practically nothing here in terms of convective development. It's just on the higher terrain, which is also typical of these thermal forcing effects here. There is one advantage to this type of setup, in that the level of predictability of the convection here is relatively high due to the terrain-induced local circulations that routinely provide updrafts in the same regions. And this level of predictability will depend on the ridgetop level winds, as well as cloudiness and soil moisture. The next highest category here is moderate flow at ridgetop level, which Banta put in this particular range right here. And what he found was the effects of solar angle become less important, and that cumulus will tend to develop downwind of the peak in the mid-mountain region if the LCL is above mountaintop, and then upwind of the peak near the LCL if the LCL is below mountaintop. And then finally, the last category here would be strong flow at ridgetop level, which would be greater than about 23 knots or so. And here, consider the fact that strong ridgetop winds interfere with the thermally forced wind systems that lead to convective initiation, so that thermally forced upslope flow becomes shorter and more disorganized. The result is that thermal forcing is just a limited factor now, and that obstacle and dynamically driven effects will tend to dominate. Our case study for strong ridgetop level flow happened to be a severe weather day, so I'll show the MCD that came out for this particular region. So we're looking here over Wyoming, and you can see a fair amount of CAPE in place, around 1,000 to 1,500 joules per kilogram, a cold front just to the north here. And next we'll look at the sounding from Riverton, which is in central Wyoming here. Here's the sounding from Riverton in the morning, and you can see it's a pretty good severe weather sounding for the west here with pretty good moisture. Lapse rates are pretty good, and the shear looks pretty good as well in terms of strong mid to upper tropospheric flow, and then you have the low-level southeasterlies bringing in the moisture. Now the thing I want to really focus in here is the ridgetop level flow, which would be approximately in this range right here, depending on what ridge you're analyzing over Wyoming. And you can see it's in the 15 to 30 knot range, but with mixing, you would mix down these winds at a little bit higher up and definitely get into the strong ridgetop level category. Here's the topographic map for the region of interest. Riverton is located right here in this lower basin area. Off to the northeast, they have the Bighorn Range over here, and then this higher terrain region extending over to the Absarokas in this region. And then southwest of Riverton, you have the Wind River Range with this generally higher terrain that extends just to the east of that. Here's the visible satellite imagery during the day, and what I want to do is start off with the surface observations to show you the environment here. And you can see these strong southeasterly winds here bringing in dew points into the mid and upper 50s into this region here. Remember, just south of this cold front that's draped across northeast Wyoming. And then what I want to show next here is just contrast this with the light ridgetop level flow, which we were just looking at. Remember, in the light ridgetop level flow case, we had convection and cumulus developing pretty much all over the higher peaks. And here we're only seeing the convection developing in specific places. So what's going on here is that the strong flow at ridgetop level over the mountains will tend to ventilate the surface as it tries to heat up. Thus, this mixes away heat from the surface. And this also prevents the buildup of a strong slope atmosphere temperature difference that would drive thermal circulation. So the stronger flow at ridgetop level will act to discourage, but of course it doesn't prevent convective initiation over the mountains. What you need is the right conditions where you have higher CAPE or higher convergence, such as this area right in here. Remember, we have southeasterly flow impinging on this area, so we have upslope flow and obstacle effects right into this region here. And you can see multiple attempts at convective initiation before we actually get some storms developing. So where the storms are going up here is along the higher terrain regions here, but again, only in specific areas where the ingredients are coming together. And this was a pretty big severe weather day. They had quite a few tornado reports out in eastern plains of Wyoming out here, just out ahead of this cold front that was coming down just like this. Now let's switch gears to a more stable situation, lee wave clouds, and consider the situation of flow nearly perpendicular to the mountain range, where the winds increase rapidly with height, and you have this stable layer with a maximum corresponding with the largest wave amplitude. And here's our diagram right here with the mountain range, the stable layer located right in here, and then these colored in areas here would be where your lee wave clouds have set up. and the wavelength between these lee wave clouds turns out to be proportional to intensity of the turbulence, which can be important for aviation purposes. Here's our example visible satellite imagery. So we're looking downwind of the Tetons and the Absarokas here in northwest Wyoming, and you can see these lee wave clouds set up just downwind of the mountain ranges that I just mentioned here. Now let's contrast that with a situation that looks very similar in that we have these wave clouds here in eastern Nebraska. It looks very similar to lee wave clouds, but since we're in eastern Nebraska, northeast Kansas here, we know there's no mountains around. So what's happening is this is actually a different type of mechanism in terms of what's producing these types of clouds. These are called stable wave clouds, indicative of regions of stable air. And the fact that they look very similar in the satellite imagery, but just keep in mind that the mechanism in forming them is very different. Sometimes you can have both lee wave clouds and stable wave clouds in the same scene. Here we're looking in New Mexico and the Texas Panhandle, and we can see lee wave clouds that are developing east of the Sangre de Cristos here in New Mexico, and then we look a little bit further south and we see these stable wave clouds that extend out well into the plains of eastern New Mexico here. And what's going on is we can see a cold front has actually just gone through the region here, moving towards the south, something like this. So just behind the cold front, we see these stable wave clouds set up and extend all the way to the Texas Panhandle here. One thing to note is the spacing here, the wavelength between the various wave clouds. And you can see these ones here in eastern New Mexico with a fairly large wavelength between them here. And remember I said earlier that these are proportional to the intensity of the turbulence. So when you see this large wavelength between the various wave clouds here, this would indicate the potential for severe turbulence. Now let's look at an example in the visible imagery where we see some indications of stable wave clouds and lee wave clouds here in Colorado, and then clear skies mostly in southern Colorado and into New Mexico. Compare that with the water vapor imagery, and now you can see a number of different waves in the water vapor imagery. It just happens to be too dry to produce clouds in most of these regions here. But this would still be an area to be concerned about in terms of severe turbulence potential here, where you see these waves that are developing, particularly downwind of the Sangre de Cristos here in southern Colorado and northern New Mexico. So remember to use the water vapor imagery as well when you do have the situation of clear skies where there's just not enough water vapor to produce those clouds. Next, let's look at orographic cirrus, and these are relatively easy to spot in the satellite imagery since they're stationary and they form along a mountain range and in fact only in the downwind direction of the range. So in this diagram here we can see this mountain range, and then you would have the orographic cirrus depicted in this region here, forming along and downwind of the range here. In terms of the conditions for development, you need stable conditions from the mountain range to the upper part of the troposphere, and nearly constant wind direction with height. Then what you have is this wave being produced by the mountain range and transmitted to the upper levels, and given sufficient moisture at upper levels, you'll see this cirrus develop. I want to make a note here of this cirrus that you see on the upwind side of the range. This may or may not be present, but this cirrus right here is the focus here, the one I'm talking about, the orographic cirrus. Now the obvious effects here in terms of forecast implication is temperature. It can have a big effect on the temperature forecast. Let's look at a topographic map for the region of interest here that I'm going to show an example of orographic cirrus. The first area that we'll look at is the downwind of the Cascades, which are located here. Then we'll also be looking downwind of the Lewis Range in northwest Montana, and then also the Tetons and the Absarokas here in northwest Wyoming. Here's the visible satellite imagery, and the various regions we'll look at for orographic cirrus The first one being over here, downwind of the Cascades. You can see this orographic cirrus that's forming in here. And one thing to note is there is a clear zone gap that's formed between the mountain range and where the orographic cirrus is forming. We'll talk about that in more detail in just a minute here. But meanwhile, let's look over at Montana, and you can see the orographic cirrus forming just downwind of the mountain range over here, as well as in Montana, where we have that thick orographic cirrus that's developing downwind of the mountains here. And the big implication here in terms of the forecast is the temperature. Consider this particular example where we're looking at the orographic cirrus forming later in the day, and that'll have significant forecast implication in terms of overnight temperatures possibly being warmer than what was forecast by the model. Conversely, if this sets up in the morning where you have the cirrus preventing the sun from coming in and warming up the temperatures during the day, that would be a situation where it could be cooler than what the models were saying in terms of the forecast temperature. So next we'll introduce a tool that may be of use in terms of forecasting orographic cirrus. A tool for forecasting orographic cirrus is synthetic imagery from model output. Synthetic imagery is model output that's processed through a separate model to produce what satellite imagery would display for a particular band. The limitations are the usual model limitations that you're familiar with, that is, insufficient horizontal resolution, microphysics packages that attempt to parameterize complicated processes, and so forth. The advantage to synthetic imagery is that it's an efficient visual comparison with GOES imagery. Therefore, simulated orographic cirrus will appear very similar to that observed in GOES imagery, and that is as regions of colder brightness temperatures that develop along and downwind of mountain ranges. There is an entire visit training session devoted to this topic. The name of it is listed here, Synthetic Imagery and Forecasting Orographic Cirrus. It's focused on using the 4-kilometer Nissel Whorf ARW model as the source for the synthetic imagery. And you can find that on the student guide for the visit web pages right here. Just look for training sessions link on the visit web pages for more information. Here's an example of synthetic IR imagery from the 4-kilometer Nissel Whorf ARW model on the left and the 4-kilometer NAM Nest model on the right from a case in December of 2013. Both models forecast orographic cirrus downwind of the Front Range of Colorado. However, there are some differences between the two models. The aerial extent of the colder cloud tops that we see in the Nissel Whorf is less than what we see in the NAM Nest over here on the right. This is due to differences in microphysics packages that you can learn more about in the visit training session mentioned on the previous slide. There's also differences in the model forecast. Note the Nissel Whorf dissipates the orographic cirrus during the late morning hours over the Front Range in this area, while the NAM Nest retains the cloud cover for most of the day. Which model came closer to reality? Well, next we'll check the corresponding GOES imagery on the next slide. The GOES IR imagery for the same time period we just looked at from the synthetic imagery shows that orographic cirrus did develop along the Front Range of Colorado and persisted through the morning hours, helping to prevent insolation and thus keep temperatures cooler. By the afternoon hours, most of the orographic cirrus has dissipated in a similar way that was forecast by the Nissel Whorf. In practice, the various model outputs can be compared with the GOES imagery throughout the day to assess confidence in particular model solutions. The main idea to take away is how easy it is to spot orographic cirrus in the synthetic imagery and readily compare it to the GOES imagery. Next, we'll look at inferring turbulence from the imagery. And for the situation of straight or anticyclonically curved flow, nearly normal to the mountains with greater than 35-knot winds at mountaintop and 75 knots at jet level, we have this configuration here where we have thin cirrus that may or may not be here with them coming in perpendicular to the mountain range, and you can get a couple different situations. One where you have this clear zone gap followed by the thick cold cirrus, the orographic cirrus that we just talked about. The other situation is that you have no clear zone gap. And it turns out that studies have shown that when a clear zone gap, which is referred to as a foam gap, exists here, that turbulence is likely immediately downwind of this foam gap. And then the other situation where no foam gap exists, this is found to be, based on past research here, that turbulence is unlikely to exist in this particular situation. Here's the visible satellite imagery showing a couple different regions where we have orographic cirrus developing. One here in Washington, the other one in Montana. And the first one we'll look at is here in Washington, where we can see the Cascade Range being right about here. And then you have this clear zone gap, foam gap, right in this region, and the orographic cirrus forming just downwind of that clear gap. Based on the slide that we just looked at, this would be a region to be concerned about for severe turbulence because of the existence of a clear zone or foam gap. Over here in Montana, we can see the mountain range oriented something like this, and the orographic cirrus is forming pretty much along the mountain range itself. In other words, there's no foam gap that exists here. So here, severe turbulence would be unlikely, and over here, where you have a foam gap, severe turbulence would be likely just downwind of that foam gap. The next type of mountain cloud we'll look at is the wall cloud. This has a number of different other terms depending on where you are, especially in Europe. You may hear this as the barrage or style cloud. And what I'm referring to here is thick, low to mid-level clouds that form on the windward side of the mountains. In other words, you have this upslope region over here, and you have persistent clouds that form on the windward side of the mountain, and then cloud-free region to the lee of the mountains, the downslope side here. And the consequences here is that precipitation may be prolonged on the windward side since it's tied in with the terrain. And in sub-freezing conditions, icing can be a problem for aviation purposes due to large amounts of supercooled water within the cloud that don't move for the most part, again, since it's tied to the terrain. Here's our example from November of 2006. And first I'll overlay the observations here just to show that we're in northwest flow over most of the state of Colorado in fairly cool conditions. There was actually snow reported underneath some of these regions here, underneath these clouds. But the wall cloud that we're talking about is pretty much in this region right in here, again on the windward side of the mountains. And then just downwind of that, on the downwind side, we have this clear zone that's formed. And again, that's not a clear zone gap like we just talked about. It's actually just downwind of the mountains here where we have downslope warming occurring here. The clear zone gap, look for the situation of winds coming in perpendicular to the mountain range. And in that particular case, we're looking at higher level clouds. Here we're looking at the lower to mid-level clouds here associated with precipitation.
We will now move into the second part of the session and start off covering destructive downslope winds. The first case we're going to look at here is for an April 1999 situation that took place on 3 days, the 8th through the 10th. It was significant in northern Colorado, east of the Front Range, or east of the Continental Divide, in that there was $20 million worth of damage done over the 3 days. As you can see through the loop, there's several hints that we have something going on in the upper atmosphere. We have 3 different short waves approaching over 3 different days, but we have a little bit different result. But the bottom line here is that we want to look for situations in the imagery that will give us hints that something is going on down below. So it's sort of by proxy. In this particular case, and in almost all cases that have to do with terrain, you're looking for persistent features that seem tied to some terrain feature. And if you look here, this is the approximate location of Front Range. If I remove that, you'll see over the period of time, I'll go ahead and move it back here and show you the approach of the first short wave on the morning of the 8th. You start to get these areas where we have these warmer and drier areas that lie just to the east of the higher terrain. Let me go ahead and erase that, and then we keep moving on, and we'll see this area right in here in particular. You'll see persistent warmer and drier conditions through here. In this case, you'll find that by looking for the darker grays right in this area where we're surrounded by clouds elsewhere. This is where the downsloping east of the Front Range is occurring right through here, and we're getting compressional warming and downslope winds in this particular case. We go ahead and erase that again and move out a little bit further, and you can see that we're still, even moving in through the later morning hours, we still have a darker area right through here, right through the core, that we want to pay close attention to. We would want to get on and look at the observations right away. As we move later in the day, we see that starting to wash out, although it's continuing up to this point, but that's because we have a cold front that has since moved through the area. If I back this up just a little bit, cold front's right here. It's progressing down to the south, southwest, and it moves through, and we lose the punch we need for the downsloping winds from the west moving over the mountains. So we go ahead and erase that on the 8th, and then as we come into the 9th, this system gets here a little bit later in the day, so it doesn't start to take place until the afternoon, but we're already starting to see hints. Again, east of the Front Range, even though we have clear skies, we're using the 10.7 micron imagery so we can tell that we have warmer and drier conditions right here, right in this area adjacent to the Front Range again. We can see that nice darkening, and by looking at the sounding, which I'll show you in a minute, we would know that we have westerly winds blowing in this area. So here we come, and now we're getting a big difference starting to show up in here. And this is a telltale sign when you're in the lee of mountains like that something is going on. Let me go ahead and erase that and move it just a little bit further. You'll see that area even persist as the higher clouds start to move in over the top. And we'll move out a little bit further, and we can still see this area poking through. We're getting enough downslope dynamics below that we're actually changing the attributes of the clouds, even though we have colder cloud tops and cirrus clouds above. It's actually showing up in that field there. Go ahead and erase that one more time and move it out just a little bit further, and we can still see some of this area persisting into the early evening period. And then we start to fill in just a little bit later on. The next day we also had a repeat of almost what happened on the 8th, although it was on the 10th that day. We had early morning shortwave come through. We had good westerly winds, and we had good support at the upper levels, and I'll show you that in the sounding just coming up. Here's a quick look at the station observations during the 8th and the 9th, and I'll go ahead and animate that through. You want to notice that there's rather sparse observations, overall when you're looking at just the METARs and stuff, unless you happen to have a mesonet in your area. So it's not always going to capture the strongest winds. So when you have conditions that look like they're going to lead to strong downslope winds, sometimes it will be caught, sometimes it won't be caught in the surface obs, and you need to do some calling around in between. That's why using the 10.7 micron imagery or any of the satellite imagery is helpful in filling in these gaps. I'm going to go ahead and just bring this back one more time, and we'll start the animation again. This is the morning of the 8th. You can see the winds coming around to the west, and then eventually really taking off and getting up to 50 knots up in the Boulder area. And then as we come into the 9th, it happens a lot later in the day, but you'll notice we only get up to about 30-35 knots showing up in the Boulder area, even though we were getting destructive winds in and around the area. Again, fill in those gaps using the satellite imagery. Okay, now here's the sounding for this particular case, and you always want to look in the upstream direction, and in this case we had westerly winds, so you want to look west of where we're getting the destructive winds along the Front Range. So we looked at Grand Junction on the 8th. This is the morning of the 8th, and there's a couple of signs here that tell you the conditions are fairly good for possible destructive winds, and one has to do with this up here in the upper right-hand corner of the sounding, the 700 millibar to 500 millibar lapse rates, and it's showing it to be slightly to the stable side here. We're just at 6, just barely under 6. That's one hint. You always want to be right around that mark to the stable side. The more stable it is, the better. The other thing is within, in our particular case, because of the height of the mountains, we use the 700 millibar to 500 millibar levels out here, right in this range. We want to look for extra stability within those layers, and we're finding that right here. We also want to look for winds over here to be right around the 20 to 25 knots or higher range at least. Any lower than that, you probably won't be able to squeeze the air fast enough and move it fast enough over the mountains in order to get the destructive level of winds, although you may get certainly higher winds. But once you get to the 20 to 25 knot range in here, and the stronger the stability within the layer, you'll be able to provide for those stronger destructive winds above 50 knots, 50, 60 knots. And in this case, we had many reports of near 100 knots at times. So you just want to keep that in mind. But the general idea here is look for stability in the layer immediately above, at or above the ridgetop level of the mountains you're concerned with, and then look for extra stability, inversion layers, and things like that within that layer to help boost the conditions a little bit more. Here's a quick look at the terrain of Colorado that highlights some of these things that we're finding in this destructive wind case. And you want to look for those same kind of things in your area. And the idea is that you want to look for rather long ranges, if you can. The longer, more linear, the better, something like this. And in this case, we're looking at the front range area right in here. And you can see how that's fairly linear through here. And that helps because you want a long range that you actually have to force the wind, the airflow over the mountains and not around it so much. The second case that's going to be coming up in a moment is actually right here. It's called the Park Range, and it's another one that's linear. It's a north-south oriented range, and it has the advantage also of being open from the west or the east if you have westerlies or northeasterly winds that can come in here, and they're fairly unimpeded by anything in front of them. So this is another area that frequently will get some kind of blowdown events. Another thing that you want to look for is if you have linear range, that's great. You want to look for cupping like this into the wind. So if you have easterly winds, this would be advantageous to keeping the wind strong on this side of the mountain. It almost acts as a focal lens to focus the winds and keep them strong and keep them convergent. If you have the same area with winds blowing from the west across it, it tends to disperse the winds on the other side, and so the winds they're not quite as strong in that particular case. There's some embedded areas here, another one down here. You see this cupped area right in here. And here's a case where if you get strong easterly flow, you're going to get destructive winds on the west side, immediately on the west side. And these mountains are very high. They all go up above 14,000 feet. However, if you get winds going like this from the west, it'll disperse it. And this is where Denver lies. So they don't get a lot of destructive wind events so much in Denver as they do Boulder, and Boulder's located just here to the north. So we have another little cupped area up here, and when you get northwesterly winds into this area, it will tend to focus things and keep things right next to the mountains here, and we get a lot of destructive winds in Boulder, a lot of damage. Even on a yearly basis, they'll get that. Another thing that you want to look for that you can't really see as well here in this terrain map is for a steep lee side slope. And I'll show you that in the upcoming schematics and conceptual diagrams, why that's important. But obviously you want to look for areas that have the very great gradient change in a short in a short distance, those would be beneficial to providing the mechanism you need to keep the strong downsloping winds. And now we're going to go over a couple of pages that have to do with forecasting strong destructive downslope winds and windstorms. In our case, we're looking at the 700 millibar level out here. Again, that's because of the height of the mountains out here. Adjust that for your area. If your mountains, top out, at 5,000, 6,000 feet or something, those kind of ranges, then look down to the 850 level, and then you might want to look at the 850 to 600 millibar level for your stability index. If you live somewhere like in Alaska where you're forecasting winds coming over the Denali range, you are looking at 20,000 feet, so you're going to have to look up much higher, maybe in the 500 to 400 millibar level. Just adjust it according to your area. But anyway, out here in the Rocky Mountains in the Front Range area, we're going to be looking roughly at the 700 millibar winds, and we're going to be looking at those to be at least 20 knots, like I mentioned before. And the direction you want to be roughly perpendicular to the mountain barrier, and that's plus or minus 20 degrees. And that's also the situation with most of the conditions that Dan mentioned before. When you're saying perpendicular, that's usually plus or minus 20 degrees to get what you need. Any more than that, the winds start running more parallel or get turned, and they aren't forced over the mountains like they should, and so you just lose the mechanics that you need to keep up for this kind of thing. You also want to determine the stability of the mid-levels, and that's what we were doing before. We were looking at the stability of the 700 millibar to 500 millibar level, and we want to look for lapse rates that are less than 6 degrees. That's just in general. And then you also want to look within that stable layer or relatively stable layer for additional stability, such as inversion layers showing up within there. And the stronger the inversion layer, the better in this kind of case. So you want to keep those kind of things in mind. You can also have areas that are slightly over, in your layer, in your 700 millibar to 500 millibar layer, that are a little bit over 6 degrees centigrade per kilometer. But if you have a strong enough inversion layer within that, that may overcome it and still help focus the winds. Again, reiterating some of the points I had brought up before, look for long mountain ridges with steep lee slopes. The windward slope is not as important. It can be a lot more gentle. We'll show you that in just a little bit. You want to look for mountain ridge lines that are rather straight in order to get the airflow to go over the barrier, not around it, and to flow as normal as possible to the barrier. And then you want to look for ridge lines also within those linear ranges that may be convex to the winds or cupped into the winds. So you have something like this, the wind's flowing into it, it's cupped, and it'll focus it, keep it focused on the other side and keep them strong. If it's concave to the wind, something like that, the winds will flow into the barrier and tend to be dispersed on the other side, so you just don't get as strong a wind. A couple of final points here. Remember that ridge lines that are parallel or oblique to the airflow are not generally areas that find strong downslope winds. You want, and also the convex-concave term is a little confusing sometimes. So basically, you want the airflow cupped in this particular case, and that focuses it. If it's bowed out like this and the wind's flowing into it, it'll disperse it. The other thing to remember is that strong winds will not reach the surface until, obviously, the low-level inversion, the one that's near the surface, is gone. Kind of an interesting situation can occur during these kind of situations. If you have a slope like this, and you have winds flowing down it, you have an inversion here. Before the inversion mixes out and goes away, a lot of times this area up here will act like the surface of a pool or something, and will actually slosh back and forth. And if you happen to have a station right at this point, right at the interface of the inversion to the slope, you'll see this area actually slosh back and forth, and the temperatures go up 10, 15 degrees, and then back down, and then back up for a period of a couple hours until the inversion actually mixes out. So it's kind of neat to see if you happen to have an observation right at that point. Here are a couple of schematic illustrations that point out conditions that are not favorable, and then we'll lead into conditions that are favorable for destructive downslope winds. This first case up here, we have an inversion layer that's actually below the ridgetop, not conducive to good, strong downsloping winds, as the winds are often forced around the barrier. If it's not too long and if they're forced up over the top, they lose some of their strength as they pass through the inversion layer, and then they gain a little bit coming down. But anyway, this is not a situation that you want for good, strong downsloping winds. So, case number 2 here is actually a case where you don't have, you're unstable up through a very deep layer. Now, where you might have very strong winds flowing aloft up here, and you may be able to bring strong winds adiabatically down, that would be the only case, the only situation in this particular case. But what usually happens is you are unstable in a very deep layer above the ridgetop level, and the winds will flow over the barrier. They'll get a little bit of acceleration as they move over the top of the barrier, but they'll return generally to the same speeds that they started out on the other side in the lee area. There's nothing to hold them close to the slope or help them to accelerate. Now, this last case down here is a situation where we actually do have a good inversion layer, good strong stability above the ridgetop level in this case, so we're getting winds accelerated over the slope, which you would as you have any flow over a hillside. And on top of that, it's getting squeezed in between this stable layer above and the ridgetop here. And so you get a Bernoulli acceleration through here, and it's forced out on this side. This also can lead to a situation where we'll have gravity waves start to form and hopefully break later on to get those strong destructive downslope winds, and I'll show you that in just a second. Here's a little bit closer look at that third case we were talking about. And in this situation, we have the flow over the mountains, and we have the acceleration, like the kind you get over any curved surface. You add in a nice, good, strong, stable layer right above the ridgetop level, and so you get this flow being squeezed between the top of the ridgeline here and the stable layer above it. You also get the waves starting to break over the mountains, or starting to build over the mountains. They're steepening more and more, and eventually, if it keeps up long enough, you'll get the waves to break out in the lee. This is a hydraulic jump area. You get that to break, so then you're actually squeezing the air between the stable layer here and the ridgetop, and then that holds over here in the lee slope on this side as it gets squeezed between the breaking wave here and the lee slope over here. This is another reason that you need a steep lee slope in this particular case, is for this kind of situation to occur, to get the wave breaking and to hold that airflow next to the mountainside as long as possible, and get that nice strong momentum flowing down the steepest slope you can. A couple of things that you can notice in situations like this that you can pick up either on the ground or sometimes in satellite imagery are these rotor clouds that form out here in the lee. Those are telltale signs that you have a hydraulic jump going on and a breaking wave over here. Sometimes you'll see lenticular clouds forming above the breaking wave here, away from the mountains. That's another sign that things may be starting to be conducive to accelerating winds down the lee slope. Also, when you're looking in the satellite imagery, you want to look for those gaps. You want to look for those downsloping, warming, drying winds. Those gaps show up. That's another telltale sign, and that's within satellite imagery. All right, here's another case that illustrates some of the points we have just talked about. This is an October 25th, 1997 case. It took place in the northern, north-central Colorado area, and we particularly want to notice this area up here in north-central Colorado. That had to do with that park range that I talked about earlier. And then another area down here, which is just west of Denver in this particular case, and we're going to be talking about the Arapahoe Basin ski area, which is a very high elevation ski area. This case was significant in that there was 15,000 acres of old growth trees blown down in the park range area up here, and it actually happened during hunting season. Otherwise, it may not have been noticed for a long period of time. But since it happened during hunting season, it actually trapped a bunch of hunters up there for 4 or 5 days before they could get out, or have people get in there to get them out, or be airlifted out by helicopter, because of the stands of trees were 30 or more feet deep in some areas where we had the blowdown. And it was old growth trees on top of that. Another reason that this case is kind of significant is that this is an east or northeasterly wind case. Most of the time out here in Colorado we have winds, generally speaking, from the west, especially at higher altitudes. So you expect to have most of your destructive downsloping winds on the east side. That would be your lee side. And that's the case most of the time. So this is a little bit unusual in that we had a very deep low to the southeast at this time, down around northeastern New Mexico, that was giving us a very deep upslope flow out of the north-northeast this way. Again, like I talked about before, this park range area up here was open to the terrain to the northeast, so that would be conducive to getting those winds to flow up against it without having anything interrupted ahead of time. This was a very strong east slope or front range snow kind of storm. They had 2+ feet in a lot of areas out here. We had barrier jet formation out here. We had cold air damming along the front range. A lot of stuff going on out there, so it was affecting a lot of people in the front range, but not the wind. The wind was all happening on the west slopes of these mountain areas, like the A Basin area up in here, and then, of course, the Park Range area here north of Steamboat Springs. And it didn't get quite as much attention just because, it wasn't as affecting as many people. But I'm going to go ahead and animate this through and show you what to kind of look for. And again, we want to look for persistent features that seem to be terrain tied. And so as I move out ahead, and you want to keep, we'll keep looking in this northern Colorado area right here at the beginning. You'll notice right in here we start to get these features right here where we have much warmer, drier conditions going on right in here, and they seem to be persistent. They're not moving with the flow. They're anchored and they persist right in this area. And this is right when we were getting the strongest winds, up to 140 knots at times, and this is where the blowdown was occurring. Down to the south, you can also pick up another feature that is a telltale sign of fairly strong flow, and at least you're setting up good strong waves and possibly getting some kind of breaking wave action going on, and that's with the waves that are showing up in this infrared imagery here. And I go ahead and change colors like this, but you can kind of see that little ribbed area growing right in here. Now I'll go ahead and erase those, and I'll move it out a little bit further, and you'll watch the area to the north and the waves, and then watch that area move further south eventually. And again, this is remaining kind of anchored in this area. As it moves further south, we continue with the strong winds. This is when the strongest winds occurred in the Arapahoe Basin. They got, again, between 120 and 140 knots. Happened to be a few people up there getting ready to open up for ski season at this time, so we had some people up working up above timberline, and they happened to catch this kind of thing, so it was kind of interesting. But you'll notice again the persistent terrain-tied features that are showing up in the infrared imagery here, which is a telltale sign that something's going on that has to do with the wind field and the flow, and you want to get on the horn and see if you can find anybody. These are remote areas a lot of times, and sometimes you will, and sometimes you won't find anybody, but it's worth trying to keep tabs on anyway. And then as the low moved further south, the area eventually washed out, and we lost the western connection. But again, we were getting that deep flow. We were getting it into a cupped area. Remember, like I was talking about, Arapahoe Basin, the range is cupped like this, so if we have east-northeast flow into that, it's going to keep it focused on this side a little bit more. and we get the strong downslope winds, although a lot of those were at or above timberline. Didn't destroy anything because you can't. It's hard to move those boulders, but and then up here we had that long straight park range that was open to the flow out of the northeast, and again we had the destructive winds. It was about normal to this range right in here, and so we had the destructive winds on the west side of the slopes instead of the east. Just kind of an interesting case from that standpoint. Here's a quick look at the surface obs in the area, and obviously a lot of times you work in data void areas, and the area in the park range that had all the damage was actually up here, and the damage and strong winds down by Arapahoe Basin was down here, and there's nothing there to report on, except we did have, again, a couple of ski workers up here that we were able to get information from at or above timberline. But for the most part, we're in data void areas, so that's even more important reason to use the satellite imagery to garner these kind of situations and indications within the imagery that something is going on, and then to also, put that together with your other observations, particularly soundings, to see if conditions are conducive to producing these kind of wind fields. And you just relate those to your terrain, which you should know very well in your own area, and come up with an idea. You might even come up with your own cookbook in your area and targeting specific mountain ranges that would tend towards this kind of thing. But this shows the importance of using other kind of observation platforms in addition to just what we're getting from the surface obs, because it's just not showing up here. All right, here's the sounding that we use for this case, and again, you want to look upstream. So since the winds were coming out of the east or northeast, as we can see over here in the wind field, we want to look at the Denver sounding in this case, because that would be the one closest to the east of us. The stable layer right up here, I'm going to go ahead and change colors before I forget, is again, we're looking at 700 millibar to 500 millibar layer, and the lapse rates are very stable, showing minus 2.5 degrees centigrade per kilometer. That's a strong indication that we're going to have conditions conducive to good strong airflow, especially if we have the ambient airflow is above 20 knots, which it is here. It's actually varies between 20 and 40 knots in this area, so we're going to find very, very strong winds. The other thing is this very strong inversion level from ridgetop or 700 millibar level on up to about 620 millibars, and this is really aiding in the whole scheme of things here. The mechanics here are really going to be conducive to keeping that airflow force below this stable layer and just above the ridgetop, and it's just going to really squeeze that together, give us a good Bernoulli acceleration, and really help us get that that strong wind flow going. And again, you want the strong or steep lee side slopes in this case to keep that air hugged down to once you get the waves to break out in the lee. So this is the kind of thing you want to look for. Keep that in mind. Apply, of course, apply your sounding to whatever level you need to in your area, depending on the terrain height. Next, we're going to be leading into a little bit of review, and I'm just showing you the Washington, Oregon area, and I just want to keep some of these mountain ranges in mind here to begin with. You know, the Cascade Range over here, and the Coastal Range over here, and the Olympic Mountain area over here, and then the Plains area over here. Just a few things to keep in mind as we look at flow over this region. And then this is going to directly lead into terrain-driven convergence or convergence zone analysis. And so you want to keep some of this stuff in mind too. And the first case for convergence zone that we look at will actually take place up here in the Puget Sound area. Here's a loop that we'll look at that has a little bit of review in it, and it's going to also lead into our first convergence zone case out here in the Puget Sound area. Let me go ahead and start the animation here. And a few things we can see is the Orographic Cirrus lining up in the lee of the Cascade Range. Dan talked about that earlier. We were also talking about lee wave formation. In this case, we have actually some lee wave formation out here, but then just to the west in the mountains proper, we actually have some mountain wave formation. And the conditions are very similar in the way they form. Here they don't move very much. They'll get trapped around the ridge lines, and they tend to, has to do with the wind flow and the amplitude of the waves over the mountains match up with the width of the base of the ridges, and they'll look like they're staying put for a long period of time, and it's also a pretty stable area. This something that you can gain or garner from looking at good visible imagery. Another thing that you can see is the cirrus streaming into the area over the top. Now, this is something we've talked about in past sessions, and you want to notice that has to do with jet level cirrus and a shortwave coming in. So you look at this marine layer that's hugged in next to the coast here, and after that moves overhead, actually that scours out that whole area. It allows for rapid evacuation upward, and we scour out that nice marine layer and fog that we did have here, and then replace that with nice clearer skies anyway for this time of year. So there's a lot of neat things out here. We're even seeing some lee wave or stable wave cloud action down here, more in the plains area in southeastern Washington and northeastern Oregon. So a lot of things again that can be garnered by this. We can see the approach of a front up here, and the cold air signature and the cloud tops over here approaching the coastline, which would further support where we have that nice jet moving through here. So just things to kind of keep in mind. You can get a lot out of satellite imagery. We're going to now shift gears a little bit and start talking about terrain-driven convergence or convergence zones. We've got 4 different cases here representing different types of convergence zones, but the idea is if you have terrain differences at all in your area, and you're not just one big flat plain, and even then you might be able to find it, you're going to have terrain-driven convergence at one time or another under certain synoptic or mesoscale circumstances. So beyond what the atmospheric physics and dynamics are for a certain situation within that big picture, you need to look at the smaller picture of these terrain-driven convergence areas. Find them in your local area, because what they really are is boundaries, and boundaries are where all the action takes place, either along them or across them. To begin with, we're going to be looking at Puget Sound convergence zone here. It turns out to be an obstacle effect kind of convergence zone and takes place in the lee of the Olympic Mountains. We'll move from there to the Denver Vorticity convergence zone, and this is a case where you actually have a mountain range such as this, where I have the long line drawn here, and then you have a ridge perpendicular to it, and you get flow from southeast. In this case, it moves around this ridge and then helps it curl in more. At the same time, you have a synoptic or background either drainage winds off the mountains or a little bit of more amplified winds due to westerlies at the mid-levels. So that's another type of convergence zone. We'll move from there down to Arizona and talk about the Mogollon Rim convergence zone, which is another case where you have channel drainage down the Little Colorado River Valley towards the Big Colorado River, and then you have flow over the Mogollon Rim, and the two meet, and you get a convergence zone formed. And the final one we'll look at is the Snake River convergence zone, which is sort of a combination convergence zone area, because it's located between two mountain barriers, or the Snake River Plain is located between two mountain barriers, and so you have a lot of different opportunities for several different types of convergence zones to take place. In our first case, we're talking about the Puget Sound convergence zone, which Puget Sound is located right here. This has to do with directed flow around an obstacle, which in this case happens to be the Olympic Mountains, which are located right in this area. You get flow from the west or northwest down the Strait of Juan de Fuca, and it comes in like this. You get The flow on the south side comes through the Chehalis Gap, and the two meet somewhere right around here over the Puget Sound area, and that's, of course, in the lee of the Olympics. And what ends up happening here is, depending on whether it's a winter or summer situation, this sort of happens to be in between. We actually get enhanced convergence right in this area, which either aided the convective parameters that were going on and gave us some thunderstorms over the eastern half of the area that tended towards where Mount Rainier is, and they were pretty strong for that area. They had pea-sized hail, quite a bit of hail, a lot of lightning and thunder, so that was one consequence. A little bit closer to the Olympics itself over here in this area where we had good convergence closer to the lee side of the Olympic Mountains, we actually had enhanced snowfall for this time of year, and had anywhere between 8 and 12 inches in certain areas, which prompted advisories, at least, perhaps a warning. So this is kind of an interesting case. It takes place in the Northwest. We'll look at a schematic here in just a minute. Here's a schematic of the situation that I was showing you before, showing you basically the same thing. You have flow coming in from the west-northwest, and it flows through the Chehalis Gap, down the Strait of Juan de Fuca over Puget Sound, and it meets right in this area near Tacoma or Seattle. Now, depending on which one is the more dominant flow, whether it's more dominant from the south or the north, this zone will set up a little bit further north or maybe further south, and they tend to migrate one way or another depending on, of course, the dominant flow. Streamline analysis is always a good place to start. It's nice to pull up a LAPS or MSES streamline analysis for the previous hour, and it gives you an idea of where you might look for convergence zones. Sometimes they're very plain and stick out like a sore thumb like they do here, and it's obvious that there's some heavy convergence going on in this particular case. We'll see some other streamline cases for other ones that are a little more subtle, but all the same, they do show hints that you do have convergence going on, and would definitely want to take a closer look at that situation. Okay, moving on to the next case. This is the Denver Vortician Convergence Zone. Obviously, it takes place in Colorado, and we've looked at a little bit of the terrain there before. Watch as this loops through a little bit, just to kind of get an overall idea of what's happening. I'm going to stop it here at the end of this loop, and we'll walk through this a little bit and see what I'm talking about. I described it as being a ridge perpendicular to mountain barrier type situation, and here we have the Front Range roughly drawn in there with the red. And earlier I had alluded to some ridges that poke out east-west from this area, and one of them up here is the Cheyenne Ridge. One of them down here is the Palmer Ridge, and it's very close, just south of Denver. And then we have one even further south called the Raton Ridge. When you get ambient southeasterly flow into this area, south-southeasterly flow, you'll get accelerated flow closer to the edge of the ridge than you will out here a little bit further east, and that causes a bending. The vectors want to turn inward, and so you get a little bit of bending, and you get the flow, nice, warm, moist flow from the Gulf moving this direction, moving towards the west. And at the same time, in these kind of situations, the setup is you usually have drainage flow off the Front Range all through the morning hours, and it makes its way slowly out to the east, and you might even get a little bit of a mesohigh tucked in right next to the Front Range itself. And sometimes this is enhanced a little bit by the upper level flow. If you have decent mid-level flow coming from the west over here, it might enhance that just a little bit, especially if you can get those winds down adiabatically. Anyway, what a lot of time happens is you'll get early morning convection, which is what's happening in this case, and things are looking pretty good right over the mountains. And then poof, those kind of go away. You can see the tops becoming really diffuse and glaciated here. Storms losing their punch as they actually move over that little meso-high area where we had downsloping, even though it was weak and drying, but it was ingesting air that just wasn't conducive to keeping the convection going. But this is a pretty typical circumstance for a setup like this anyway, so you know you have flow this way off the Front Range mountains, even though it's weak flow. At the same time, the overall ambient flow, synoptic flow in the areas from the southeast or south-southeast, and you can see that in the cloud pattern here and the cloud streets down here. And we can already see how this DVCZ is setting up right here with the leading edge of it just starting to curve in and push into this. We're getting a little bit of enhanced convection along the edge of that. This is not exactly the same thing as a Denver cyclone, although a Denver cyclone may actually end up forming because of this. And you can actually see that we're kind of getting a little bit of indications that we might get a Denver cyclone, but they're not the same thing. Anyway, we're getting that push from the southeast as it's curling around. We're getting the higher, warmer dew point air moving in this way. At the same time, that's butting up against the dry, warm, dry downsloping air that we've had all during the morning and into the afternoon hours. And so we get enhanced convergence, and then boom, the big storms go up later in the afternoon. This is October 4th, 2004, and these storms produced some quite large hail and 12 tornadoes. It was pretty significant, and it is in October, which is late season severe for us. It's not unheard of or anything. You usually get that late season October severe a little bit further east. So you want to look for a situation like this, which can actually give you those springtime or early summer conditions here in Colorado, and this is one of those things that you benefit from. So you want to watch for conditions that produce these convergence zone, because if you can get these storms to go up and stick along them long enough, that's when you get the best severe weather, in this case 12 tornadoes. Again, here's the quick look at the streamline analysis, the yellow line representing the Front Range area. And even though this is a little more subtle than what we saw in the Puget Sound convergence zone area, we are getting indications that we are having convergence in the lee of the Front Range, or lee of the Rocky Mountains. So you want to pay attention to this. This would prompt you to look a little bit further into it if you weren't already expecting this to happen earlier. Continuing further south, or southwest as it were, we're going to be talking about the Mogollon Rim convergence zone. And the Mogollon Rim is a geographic feature that runs through the central part of Arizona, something like this, and then off to the southeast. And what we have just to the east of this area is the Little Colorado River Valley, and so we'll often get morning drainage that flows something like this, and it's flowing obviously up to the northwest towards where the big Colorado River Valley area is up here. So you get you have a couple of things going on here. The setup is you want ambient or synoptic southwest flow over the area, and that's picked up very easily in the Cloud Street formation here, that we do have south-southwest flow into the area. We also happen to have at the northern end of the Mogollon Rim, or near the northern rim, we have the highest mountains here in Arizona, and so they obviously often will produce early convective initiation. And you know, you have an elevated heat source, you get early convection off this, and you can see that right here. And then you see the storms actually progress, dissipate, and regrow as they move down this area, down the rim area, and that's because it's moving along the convergence zone. I'm going to go ahead and erase those arrows and stop this to show you a little bit better of what's going on and some things to look for. Again, we have the early convection going up on the higher peaks, and they anchor that northern end of the Mogollon Rim, which runs something like this. And then as that storm grows, you want to notice the backside of it takes on a very linear, very straight characteristic. And actually what that's doing is that's mirroring the Mogollon Rim to the south-southwest area. And anytime you see a feature like this in convection, a very linear, hard feature, especially on the back side of a storm, or the side of the storm, you can bet that it's being forced or anchored by the terrain in some fashion. And in this case, the difference between the edge of the higher land here and the storm here, that's right where the convergence zone is right now, and is pushed out just slightly to the east of where the Mogollon Rim is here, just a little bit further west. So as we progress on, we see the first storm go up, put out a little bit of a outflow boundary, which butted up, was reinforced and butted up against the Mogollon Rim convergence zone, which is already set up. And then we had reforming of the storms a little bit further south. And you can track those down here. And as a matter of fact, this is the area where the storm got most intense. We had flash flooding, and it was, of course, the storm was able to move right along that boundary and continue to keep the baroclinic differences going on, ingest the baroclinicity, and also ingest the additional vorticity from the storm, keeping it tilted, keeping it rotating a little bit, and was able to get some marginally severe size hail, up to 1 inch in size. And again, there was flash flooding, and there was also several attempts at putting down a tornado, but it just made funnel cloud status, never really got a tornado on the ground. But that's pretty good for Arizona this time of year, and I mean, that's a pretty decent storm for this area. So you want to keep this in mind. That's what a boundary can do. Find those convergence zones. You're looking at a boundary. It helps. Again, a cursory look at the streamline analysis. In this case, the yellow line is the Mogollon Rim, and we can see even early in the morning that we're having definite hits of areas of good convergence starting up, which again would maybe alert you to take a closer look, especially in conditions where you expect that southwesterly flow in this particular case, and that's something that definitely can start setting up the rim convergence itself. So take a closer look. For a final look at terrain-driven convergence, we're going to be looking at the Snake River Plain convergence zone. And we can see this is a fairly complex type of situation where you can get several different synoptic or even mesoscale setups giving you different types of convergence zones. One type would be having a northwest flow or drainage flow off the Rocky Mountains there, and then having a southeast or southerly flow off the Caribou Highlands down here, and of course moving towards each other. They'd meet somewhere in the middle and you get a convergence zone. Another case where if you have synoptic or background westerlies and we get the flow up the Snake River Valley here, at the same time you have maybe have a drainage flow off the mountains either to the north or to the south, and you can get convergence zones set up either on the north or the south side of the area, depending on that. You can see that there's a lot of different combinations here. Our first look at the convergence zone is actually going to be a winter case, and this takes place on November 26, 2005, and of course the Snake River Plain area is roughly right in this area right here. Something that we want to think about in this particular case is that we just had a front move through. We're on the back side, and we're starting to get general northwesterly flow behind this. So again, when you think about what we saw before on that schematic, we're getting northwesterly flow over the mountains. That may actually enhance any drainage flow that we may have had. And also some of these mountains, because of the way they're oriented, the valley and ridges are oriented something like this from northwest to southeast up here, and then down here on the southern end they're roughly south to north or so. So if we're getting northwest flow in this particular case, some of that's going to be directed and channeled through those valley areas and maybe enhanced a little bit like that too. Overall, the ambient flow through the valley area was actually from the west, so we had a westerly flow through the valley. we had this backside northwesterly flow over the mountains, and of course those two were meeting on the north side to begin with of the Snake River Plain to give us a convergent area. Now, what you want to watch for in this particular case is the storm top divergence, or the cloud top divergence. We're not looking at convective storms in this particular case, but you want to watch for that right in here. And I'll let that roll through once and see if you can see it here, and then I'm going to go ahead and speed it up a little bit more and see if you can notice the divergence, heavy divergence taking place at the top of the clouds here, right through this area. And as a matter of fact, even at the lower end, you can see lower clouds sneaking out here to the west, on the western side of the valley. All those are indications that it can be inferred by looking at the proxy measurements here at the top, that if you have divergence at the top of the cloud, you have convergence below the cloud. In this particular case, the models were not indicating any type of heavy snow. As a matter of fact, it was maybe an inch to a trace was the official forecast through the models. But what happened in this area where we're getting the heavy divergence showing up in the cloud tops here, and we had the formation of the low-level convergence zone, we actually got 6 to 8 inches moving through the Pocatello area, and the convergence area started up here on the north and just drifted slowly to the south. So anytime you see a situation like this, you would really want to look for enhanced convergence, either showing up in your radar imagery, switch it over to clear air if it already isn't on that, get a little help from that, and then of course if it starts precipitating, it should be no problem. Call around and find as many obs as you can, and of course if you have a local mesonet, that helps out a lot too. But all these things, all these data platforms can help support each other, so just keep that in mind. Again, another look at the streamline analysis. This is another subtle case, but we definitely see the north-northwesterly flow over the northern part of this coming out of the Rocky Mountains, and we have the westerly flow up the valley itself, and so we're getting a convergent area starting to show up even in the streamline analysis. And again, it's a little bit subtle, but it's definitely showing up there. You want to take notice and look a little bit closer if you see something like this happening. Okay, here is a case that took place on April 28, 2003. Again, we're looking at the Snake River Valley right up here. It's in Idaho. It's April 28th. For a severe weather event, this is pretty good. It's an early season type of event, and I'll just sort of walk you through kind of what happened before the event and right up to the time that we get good convection going on. Early on in the day, we actually had some, and wasn't quite an MCS, it was just a shortwave moving through, which gave us early morning precipitation, and that area moved off, that little shortwave moved off into western parts of Montana. At the same time, left behind, we had cool, moist air moving off the Rocky Mountains with the drainage, and it just continued to move further south, and it was really impinging on the very southern edge of the valley through most of the morning. The models were actually telling us that this area would lift further north during the day, and by early to mid-afternoon would be actually well up into northern Idaho, into Montana. That is not what happened, however, and that was supposed to happen in advance of this approaching shortwave down here, which we can see the leading edge of it. You can also see early convection going up on the higher elevation ridges down there in northern parts of Nevada and southern parts of Idaho. But that did not happen in this particular case, and what did happen, in fact, is we had warm, dry air moving up this way. The Caribou Highlands sit something like this. We kept the cool, moist air on this side. Now, while this isn't exactly a typical dry line setup like you get out in the Central Plains, this is, however, a boundary setup, and we were able to reinforce this boundary and keep it right along the southern end of that valley, right against the Caribou Highlands, which is right where I have this line drawn. So we had convection going up. Everything further to the east, as it moved out into the cooler, more stable conditions of the valley, you can see that those storms, really quickly died out. The tops become all diffuse, glaciated again, and weaken. The only two storms that maintain any strength at all are the ones that are a little bit located further to the east, and even this storm right up here ends up dying off fairly quickly, and leaving us just with this easternmost storm right here, which became quite severe. Again, we had severe size hail in the inch to inch and a quarter range, and we actually had a tornado produced with this. There were several attempts at tornado production early on, and we finally got one about midway through the event. But as you can see, that was the storm that maintained its position right along the boundary itself as it moved up, and was able to, of course, keep that baroclinicity and just that additional vorticity for the storm, helping maintain it for a longer period of time so we could get that severe hail production. A couple other things that are of interest here is as the storm grows, when it's actually in front of any of these mountain ridges here, what ends up happening is this storm took on a very HP sort of look to it. And then as it moved out into the valley area, like right here, we actually get these inflow feeder clouds starting to form. If you can see those right here, we've talked about those in severe weather before. They generally start to form to the east or to the right of the flanking line in a storm relative sense. And anytime you see this, you can count on the storm going through an intensification period, or it's reaching peak intensity. And these storms would take on a very classic look as they moved actually in front of the valley area, and we had a little bit of an enhanced directed flow up those valleys, helping give this a notch look and helping further enhance the vorticity and the spin, especially at the lower levels. And then as it moved back in front of the ridge again, it'd take on an HP characteristic, and then as it moved back in front of the valley again, it would get that classic look again, and this is right where we got the tornado produced. So very interesting case, but again, this one storm was able to latch onto that boundary and take advantage of all the physics and dynamics that go along with that, and maintain itself for a longer period of time and reach severe levels. And the final streamline analysis, again, these kind of things are kind of handy, but in this particular case, we're talking about flow out of the south ahead of that approaching shortwave that we had over here in Nevada, and at the same time we had that enhanced cool moist air left over from the shortwave earlier in the day, which would have also been aided by the drainage flow off the mountains itself. And we maintain this boundary right on the northern edge of the Caribou Highlands, and this is right where that storm latched onto and took advantage of it and moved right along it over a couple hours period of time. Here's a final look at the convective case we were just talking about and the convergence zone setting up in the Snake River Plain. And indeed, this is 21Z, and the models were saying by 21Z that the overall synoptic pattern should have had the warm, dry air pushed up all the way over and through the Snake River Valley up into northern Idaho and the Rocky Mountains. But as we can see in this case, that clearly wasn't the case. We still had the northerly flow and the cool, moist air pushed all the way down against the southern portion of the Snake River Valley, or the northern part of the Caribou Highlands, which runs right through here. Here we have the warm, dry flow moving through that area and through those valleys, and the cool, moist air on the other side giving us that nice baroclinic boundary to work on, and that storm latched right onto this and remained severe for a couple hours. So again, convergence zone equals boundary equals good weather phenomena. You want to pay close attention to these kind of situations. Normally this would be the section where we had a few quiz questions. However, obviously we can't do this without live teletraining. We will, however, go over a couple of review cases here just to show you some things of worth and to remind you of what we've covered in this session. Okay, here's just a quick look at the terrain to remind us all of what we're looking at in the next couple of cases here. We've got the Colorado higher mountains here represented in the Front Range, Sangre de Cristo Mountains, the San Juans over here, the Colorado River Valley, San Luis Valley, the Gunnison River Valley. We've got a lot of low areas. The Colorado River Valley continues here through Utah, and then of course we've got some more high mountainous areas over here. Anyway, we've got a lot of situations overall to give us drainage flow, drying flow over the mountains, but a lot of terrain differences. And again, that's what you're looking for in your area, are the terrain differences. And they don't have to be as dramatic as this either, where you go, and rise up 9,000 feet all of a sudden. You don't need that kind of thing. It can be very subtle sort of situations where you're just going from some hills like here in western Utah down to the plains. This is a salt flat area in Utah. It can be even more subtle than that. Here's the Mogollon Rim area that we were talking about earlier that follows down like this and continues down into the Little Colorado River Valley here. That's not overly dramatic, but it's certainly enough to give us a convergence zone kind of stuff. So anyway, this is just a quick look at the area that we're going to be looking at in the next couple of slides. Like I said, normally we would be asking you questions about these kind of cases, but in this particular one, we're just going to point out some of the features that you should have seen or pointed out had I asked you those questions. It's a case that takes place on November 27th, 2006, and I'm just going to let it run through here just for a second, and then we're going to step forward and see what we can see. A couple things that you want to notice as we move on in the day. Here further to the south, here's the San Luis Valley that I was pointing out before, and you can see that it's clear here. And that's because we have this higher range of mountains further to the southwest, the San Juans, and we're having flow over this way, and then we're having downsloping and drying here, which the San Luis Valley is often dry and clear because of that kind of situation under these kind of flow situations. Another clear area that's showing up is actually on the Palmer Ridge over here. And that's actually for different reasons. As I move this backwards, you can almost see it outlined pretty well where the Palmer Ridge is, and that's because we actually have low cirrus fog conditions over here in eastern Colorado earlier in the day, and the higher land area of the Palmer Ridge is actually above that, and of course it's clear and dry at this time. So there's a couple things that you can garner just by looking at the imagery that way. Okay, then we move out a little bit further, and we see this gap right here showing up, and this is on the eastern end of the Gunnison Valley area. And one thing that we have going on, we actually have a wall cloud or a barrage cloud here on the southwestern portion of this, and we have a little bit of snow going on at the time. At the same time, we're getting a clearing or a gap, foam gap, forming in the lee right here, coming off the highland areas right here. And then, as we move even a little bit further to the east, we have Orographic Cirrus going on. So we have a bunch of things that we've talked about before, all going on in this one picture at the same time, which is quite interesting. You also want to look for the wave cloud production. We've got good waves sitting down here in southeastern portions of Utah, northeastern portions of Arizona, and then also up into Wyoming. We can see those forming up here. And again, you want to notice the rather long wavelengths we have associated with those. Long wavelengths, of course, indicating or inferring that we have good turbulence going on. And again, when you find the strong wave level of these, you often want to look below where the biggest waves are, if they're being produced that way, because as they dampen out, they'll become shorter and sometimes more amplified before they die out against the terrain. So you want to keep that in mind. But anyway, long wavelengths associated with these equals turbulence. Down here in northeastern parts of Arizona, we've got some clouds that are taking on very short wavelengths, it looks like, and even down here, and those would indicate that the turbulence is relatively small at that time. And in our final case, we're going to be looking at a October 20th, 2006 case and loop here, where we can get a lot of value out of what we can see just in the visible image itself. Normally I would be asking you to tell me what you see and why it's there, but in this case we'll walk through and see what we can find together. Early on in this, you can see that we have this area butting up against the windward side, the west side of the Front Range. Remember, this is where the Front Range of the mountains, Rocky Mountains, are up here, and this is a wall cloud or barrage cloud like Dan was talking about earlier. Another thing is we've actually got a smaller wall cloud or barrage cloud down here, but you'll notice it is smaller, and the reason for that is the Sangre de Cristo Mountains are oriented more northwest to southeast instead of being north-south, and with the flow being more straight westerly in this particular case, we get a larger barrage cloud and a little bit more snow production up here to the north than we do down here to the south because of the orientation of that mountain range. We'll go ahead, and I want you to keep track of this area too over time as we move through this, because this is a terrain tide feature that is very persistent and stays. You can see these drying areas staying there for prolonged periods of time because we are having westerly flow over the park range, which we talked about in an earlier case in Colorado with that strong destructive downsloping. This case, the winds are coming from the west, though, not from the east, and they're giving us that nice area right through here where we're getting strong, very strong downsloping winds. I don't know if they're severe at this time, but it's definitely a case where we're getting strong downsloping winds, and it just stays right in that area. Again, look for persistent terrain tide features like this. Another thing that we can see is, I'll move this back just a little bit, on the other side of the wall cloud here, a lot of times we'll have Chinook winds coming down the Front Range, and we do have a short time where we're seeing a gap form in here, indicating fairly strong drying winds in this area, maybe some low-level wind shear for sure, maybe even some mildly severe winds associated with this. But there is a change coming. This is a true gap at first, and then this transitions right in here. We're still seeing a gap, but that's actually not a gap caused because of the downsloping winds in this particular case. What has actually happened is we had a front that was up here in Nebraska, northeast Colorado, and it backdoored itself something like this, and has been starting to work its way down the Front Range, and will continue on. You can kind of see how that continue to move like this to the south. The reason that you get this bulge of the front like that is that you're trapped between the mountains here on the west. You have the big low sitting somewhere out here to the east, and you get the flow pushed around the backside, right towards where the front is, and because of the squeezing between the low and the mountains over here, you'll get this bulge where you have this increased speed right here, and this is a very typical phenomena when you're trying to force wind between two structures, and obviously you get an acceleration as it's being squeezed through. We've seen illustrations of that, just looking at destructive wind potential in the vertical. This happens to be a more planned view where we're looking at the flow in the horizontal. But it's the same idea. And we'll go ahead and we'll back this up one more time, and we'll see if we can see anything else of interest in here. We actually can see some waves starting to produce on the top of these, and they're standing up late in the day, of course, as we're getting that very low light. And those are indicative of flow over the mountains and giving us some kind of turbulent flow anyway, of any kind. Anyway, there's a lot of utility just looking in the visible image in this particular case. Then you can go back and match it up with all the OBS or even the model data and see how well they're picking up on these kind of things. And of course, you can always fine-tune, especially the timing, but both temporal and spatial things by using the visible imagery or the infrared imagery, whatever you can, to sort of use it to piece together things in between situations. So with that, that's the end of this session. Thank you very much.